Okay, so good afternoon, everyone. Welcome to our session. This talk is about a hardware-supported control flow integrity. We name it as policy-agnostic control flow integrity. This is not a new topic, but it's been a very hot topic recently. So we're trying to tell you more of our research outcome in this area, especially to involve hardware in the whole scenario. So before the talk, I would like to introduce myself and the other two speakers. My name is Yier Jing, and I'm from University of Central Florida. I'm also a researcher in the Cyber Immunity Lab. And the other two speakers, one is Dean Sullivan, and the other is Orlando Arias. They're all from University of Central Florida. And you can tell that we wear all the coats we have because we've been in Florida for too long, we almost forget how to survive in winter. So going through the talk, so this is a high-level outline of our talk. So we will introduce the motivation and the runtime attacks, and also then we will discuss the defense against code reuse attacks, and then our work in hardware design requirement, and the core part, the policy-agnostic CFI control flow integrity. So before I'm going inside the, wait, why is this not change here? Oh, good. So before we introduce the key techniques, so we want to discuss the motivation. The motivation, I mean, the high-level motivation is very simple. We want to protect all the native codes. So one thing we want to discuss first is that we have been for many decades of runtime attack the arms race. And starting from the 1988, the first internet worm, and then we have the code inject attack, return to libc attack, and on and on. And then in 2007, they come to the return-oriented programming. It's kind of like open a new arena for the attack and defense. And the multiple defense solutions have been proposed, and they all been bypassed, and then new solutions have been developed. So even though it's been like decades in this area, we still see a lot of very recent examples that people using this return-oriented programming, or we call the code reuse attack, to compromise our modern system. And this is the 2013 case, and we have the 2015 case in the Black Hat presentation. And even in this year, the Cisco router exploits, and the government kind of like trying to target the human rights groups. So as we want to say that this area is a very interesting area. It's been investigated for so long, but we keep on finding some new weakness in our new defense solution that people can bypass those defense solutions. And so again, another high-level thing, so that we want to see that we know that this is a high-pack impact. And we also, not just the academic, the industry also proposed so many solutions. Like these are a list of their tools provided. But I mean, very sadly that these methods have already been proved either can be bypassed or not sufficient enough. So this eventually, as we said, this arms race is a very interesting attacking scenario that we keep on come up with new defense, but new offense method seems even pop up faster. So again, this is we give a very high-level summary of what have already been proposed. So people always ask, oh, this is a very hot area. People propose so many solutions. And this is a very high-level summary. From defense side, we have so many CFI, rope guard, bind CFI, a bunch of them. Some of them from academic, some of them from industry. However, for the attack side, we have so many attacks methods also being proposed to either bypass or to compromise the whole protection solution. So after decades of this arms race, we are still seeking practical and secure solution. And this is the I would say the beauty of cybersecurity research topic, that some research topic we may find the fundamental solution, but not on this one. So that's why we keep on come up with new idea, and our research is trying to provide, from the hardware perspective, some fundamental solutions. So going further, discuss what runtime attack would be. So first, it's some like background, just for your information. If you already know that, you can skip this slide. So first thing is that we call code inject attacks. So what's a code inject attack? So we have basic blocks there, and the attackers can leverage some of the design flaws. For example, like buffer overflow. It's a very popular bug, and then the attacker would inject a malicious code there. So then they would change the control flow and to point to the malicious injected code, so that they can do anything they want to compromise the system. But this has been protected nicely by a very simple solution, the DEP, the data execution prevention. So then come up with a code reuse attack. This time, since the injected code will not be executed, so the attacker will change the control flow and reusing some existing code block there. So in this way, they can build up the functionality. They don't really need to rely on any of the newly injected code, but just reusing the existing code, but just organize them in the malicious way. So this is the official name is we call the return-oriented programming, or it's we call the prominent code reuse attacks. So, and it has been proved to be Turing complete. So that is really like horrifying people, because people sometimes argue that since you can only use existing code, maybe you cannot do anything you want. But people have proved that, okay, it's Turing complete. So before going deep of the ROP attack, here is some like basic steps that how you need to perform a ROP attack, and there is some of the terminology that we will use on and on. The return instruction, the basic block, or the instruction sequence chain that we're using as gadgets, we combine them together. So again, so what's the threat model here? So what are we really trying to protect here? So in our work, we first assume that the application is protected by DEP. And the attacker knows the memory layout. It's transparent. But what the attacker can do, first the attacker can disclose the readable memory, and then the attacker can manipulate the writable memory. So this is the baseline. This is a very like low request to attacks, that if the attacker have this capability, that we believe that it's a reasonable attack model. And then comes our solution that we want to defend against the code reuse attack. And Dean will pick this up.
Okay, so without belaboring the point, just for some background information and completeness, there's sort of two defenses against code reuse attacks. And you can either apply randomization or control flow integrity. Randomization is a great defense because it has really low performance overhead and scales well with complex software like operating systems and browsers. However, it's vulnerable to information disclosure and requires a high amount of entropy from sort of some brute forcing style attack. Control flow integrity, on the other hand, offers formal security guarantees. But there's some trade-offs associated with the associated analysis to build a control flow integrity policy that requires trade-offs in performance and security. And it's also challenging to integrate in complex software and to cover completely an operating system overall. Randomization ultimately is vulnerable to memory leakage. It's both direct and indirect memory disclosure. will allow you to break sort of the most fine-grained ASLR schemes to date. And this is basically just reading a direct code pointer in a code page or leaking a code pointer from a data page, such as a stack or heap. This is trivial to do and has been shown to be trivial to do in JIT-style code, like in a browser in your Firefox. And our collaborators have sort of examined that extensively and shown that current randomization defenses or fine-grained randomization defenses are actually vulnerable to this. So this is the current state of the art for randomization. So we're going to go ahead and start talking about the requirements, right? So what you have to sort of solve if you want to build some hardware defense. But before we do that, I just need to sort of get a baseline for everybody on what control flow integrity ultimately is. And it is effectively just restricting control flow to benign and correct targets. And the intuition is very straightforward. Code reuse attacks divert control flow from benign and direct targets. So presumably, if I have a great CFI policy, I'm going to be able to detect some control flow hijacking. This is, again, a provably correct security mechanism with a powerful attack model in the sense that I allow the attacker access to complete memory and allow him access to write data pages that are writable and to read code pages, so he can actually look at where functions are in the program space, and so we sort of don't assume that randomization is in place. It also provides deterministic protection at runtime. So the basics are very straightforward. We have two basic blocks, and what we want to do is from the control flow graph, we want to build a sort of labeling mechanism that determines where to and from these control flow blocks can redirect control. So in this case, we have this node label A, and we're going to check at exit if it's targeting its intended path. Otherwise, it's going to throw an error if it targets a separate path. Of course, the issue is that control flow and graph analysis is in general undecidable. So what you do is you typically do what's called a points to analysis, and this is conservative. The intuition is that you don't want to intentionally under-approximate the control flow, the points to analysis, so that you have a more precise pointer set. Rather, you're going to over-approximate it to prevent breaking the program. What this leads to, though, in terms of the issues with CFI is that the precision of the control flow graph analysis actually determines the security of a CFI policy. So ideally, we'd like every edge in the control flow graph to be unique, so that you can't sort of arbitrarily redirect control or bend control flow within your CFI policy. So as an example of this, we can have some sort of static analysis that's flow and context sensitive, where we can recover completely the intended control flow targets at a particular point. However, this requires many CFI checks at that instrumentation point, and basically is going to degrade performance overall. So as an optimization step or a concession, we merge these labels, in this case 4 and 5, from node B, so that we have a single label and we reduce the number of checks we have to perform before each control flow transfer. I mean, ultimately, this is going to this is an instance of where the CFG precision reduces the security, because an attacker can redirect control flow to labels where the merging has occurred. In this case, I can redirect control if I find some vulnerability within node C to node D, or just back to node C again to perform some loop operation in my code reuse attack. What we found is that a dynamic points to analysis actually kind of resolves this issue. And what that effectively is an estimate of the number of runtime branches that can be referenced at a particular indirect branch site during runtime. And the method is we just insert an indirect callback, at the indirect branch target site to a routine that tries to match its points to set. And if we find a match, then we sort of count that as a reference within the valid points to set. And we found that basically during runtime, 90% of the dynamic points to sets were singletons. So the over-approximation in static analysis can be reduced to unique branches if you incorporate a dynamic points to analysis into your control flow graph construction. Of course, this is limited by the execution path coverage, right? So it's sort of undecidable that a program will halt, and so we can't be guaranteed that we'll cover the entire execution trace of the program. But given this, we can sort of recover more CFG precision overall and prevent this sort of style of control flow bending within the policy itself. So ultimately what we're doing is we're protecting certain types of instructions. And we're only protecting instructions that are dereferencing memory indirectly, right? Direct code pointers are not something that we're concerned with because code pages are not writable, right? So, but this is an issue for instrumentation. So 15% of the branches are indirect given in a general case, in a general execution trace of a program. The large majority of them are returns and indirect calls. But there's going to be some jumps as well, which amounts to billions of executed branch instructions. And if we're going to do static instrumentation, where we have a function call, a return, or a jump, and we need to sort of instrument the code to do a CFI check, where what we're doing is dereferencing from the target destination, the label, and then we're doing a comparison prior to transferring control, right? That this is going to incur a significant amount of overhead, both in instruction latency and instruction size. And on average, that degrades performance pretty rapidly. So what we measured is that we have some average of 35% slowdown if you're doing these styles of checks across these different types of CPUs. So we have some server-in CPUs and some more high-performance i7 CPUs, and the performance degradation is pretty constant across them. There's also some other issues associated with different elements within the microarchitectural stack. So I-cache pressure reduces due to this instrumentation pretty significantly. And the degradation in memory access latency is the one that we're most concerned with, right? So dereferencing memory, right, is going to basically occupy a lot of the overhead, and it's going to dominate that. So in a sort of hardware-based solution, you're going to want to try and reduce that, right, by adding potentially dedicated elements, storage elements, to maintain your CFI metadata that is used in checking your CFI policy. Finally, there's some other issues with label granularity that need to be resolved and pose issues for a CFI policy overall. So ultimately, calls to shared objects cannot be recalled. These are external objects where I'm like sort of linking in something externally when I'm compiling it. And the idea is you don't really know how to label this. You can't actually affix a label to this at runtime because multiple other processes are going to be trying to access this, right? So process A wants to, get some function from libc, and process B wants to get the same function. So how do I label those? And that's the basic issue. So the solution to this, traditionally, has been just to apply a single label to all of those external functions. Of course, this is not ideal because we can ultimately just redirect control to all of those labels because it's just a simple CFI check. So this is an example of sort of some concession you have to make based on some limitation in the control flow graph analysis coverage that some dynamic points to analysis can help and to recover and resolve ultimately. So these coarse-grained CFI policies sort of amount to or reduce to generic abstractions on the check. So for instance, you can only return to a call preceded instruction. In this case, the ret will either target these, and these are all great, right? But if I jump there, then nope, I can't do that, right? And so for forward edge policy, something similar occurs. I can only target forward edges, and it will trigger a fault if I target something other than a function entry, right? So this sounds great, right? But in the long run, researchers sort of determined that this isn't really great. There are too many call sites available. The heuristics associated with like the length of the number of returns executed prior to executing a system call, or too many indirect jumps and calls, all basically provide wiggle room for me to sort of bend the control flow within these policies and around these policies. And there's been a significant amount of work done demonstrating this. And the list goes on. I basically just highlighted the ones that I think are the most interesting. So, for instance, Coop is incredibly difficult to solve, as in general, no CFI defense, not even LLVM's vtable verification, which does very, very fine-grained class hierarchy distinctions between virtual table function calls, can't handle Coop. So this is like one issue that still is sort of open for research. So as a final thing that we need to sort of think about when we're talking about labeling is returns. So these are notoriously difficult to manage because you could have two functions targeting a single call site. And my control flow graph analysis is basically going to recover this sort of label 1 and label 2, right, as its points to set, okay? Now, imagine that I make a call from function A and then redirect back to B. This is valid within my control flow integrity policy because the points to set is actually, label 2 is valid within this set. So this basically allows granularity in your return address protection. And a shadow stack actually solves this, right? A shadow stack tightly couples call return pairs. Basically, it guarantees that you'll only return to your most recent call site, okay? But this, unfortunately, incurs some sort of overhead. So while ideally, I would like to implement a shadow stack policy, you're going to have to address some issues with memory hierarchy, latency, and bandwidth, and sort of nested function calls. So just some basic analysis in some generic environment. We've done some analysis with the memory hierarchy bottlenecks, and sort of read latency is kind of stable and it's not very high, right? And if you tune read latency, then you can get a significant improvement in the overhead for your shadow stack implementation, but you'd have to do that custom, right? And we want to sort of avoid. Nobody wants to sort of go in and tune every sort of program they've ever written. What about libc? What about, it's too much. And you can see here that the degradation in performance, which is the red line, sort of drops off significantly at around 20 nested function calls. And so this is a typical sort of behavior that's going to affect your shadow stack overall. Surprisingly, though, these two works right here, I need to include these two pieces of research because they're great, is they actually say that traditional shadow stacks only incur 12% overhead. So there are optimizations that you can make to reduce what we've shown here. And LLVM safe stack, which is a new protection, it's just being incorporated into the LLVM stream, actually only incurs a 0.1% overhead. Unfortunately, despite the reduction in overhead, they've done that at the cost of security. And so our collaborators, who unfortunately couldn't be here to speak about this topic, have investigated this and found that you can in fact break CFI implementations that are using software shadow stacks. And one of the reasons for this is that they optimize compiler critical CFI pointers that are spilled onto the stack. And they're able to use an overwrite to corrupt that spilled pointer. At which point, when the CFI checking mechanism starts to work, it doesn't realize that there's a malicious CFI pointer in the stack. So this is actually shown to bypass this IFCC and vtable verification implementation for SafeStack. And given that, we have the sort of overview is that we have these forward edge policies that are really great now for CFI. We have Google's VTV and IFCC, Safe Dispatch, which can really, really generate some fine-grained CFI policies for C++ applications. And the assumption is that backward edge CFI through shadow stack protection will completely solve this issue, right? We don't really have to think about control flow hijacking anymore. We just use VTV in combination with some software shadow stack, like for instance, LLVM's Clang, except tomorrow you're going to hear a talk, and I recommend you all go there, where some researchers, Anes Goktas and Herbert Boss, I think from VUSEC, will be presenting a bypass of Clang's safe stack. So what this sort of shows is that it's like sort of the underlying assumptions behind software shadow stacks and being able to maintain isolation within the software stack is going to be problematic overall. We want to kind of address that issue. So with that background information and sort of the motivation details, we're going to try and introduce at a base level what our implementation actually is. We call it HeyFix++. It was presented at DAC in 2016. We also presented a prior work in DAC in 2015, which called HeyFix and won the best paper there. It was with our collaborators here. And the outcomes of that are that we have some really stateful policy-agnostic CFI implementation for both backward and forward edges. We've created some implementation that doesn't require source code modifications to instrument your application or to recover a CFG. We have a precise CFI policy enforcement for both forward and backward edges with no heuristics incorporated, and we try to limit the amount of concessions. And we'll sort of go over what those concessions are, but we think those are good. Anyway, we also have some isolated memory for CFI, metadata. It turns out that when we actually incorporate the entire system, it incurs less than 3% overhead, which is as a worst case, which is pretty good in our estimation. And it supports multitasking and shared libraries, so it's practical and can scale to complex software. We also have a mechanism for interoperability with legacy code, which is kind of important because not everything that you're executing on your system is going to be instrumented with CFI protection. So at a high level, the state model has an initialization phase, which is in an idle state and is checking for a CFI disabled bit. If we have CFI enabled, then we just enter CFI execution and move forward. For our forward edge control flow state model, it's, again, very straightforward, which is one of the benefits of, I think, our implementation, is it's sort of kind of intuitive how you would implement this, is we're in a CFI execution state. If we're executing just instructions that are non-branching instructions, right, we just stay in this state. We don't need to do anything. If we encounter a call or a jump, then we need to save these call targets, right, so that later on when we actually enter the target, we can do a check, right? So upon execution of the call and jump, it's just simply, does the check work out? No? Trap the program? If it does, yep, you're good to continue execution. The same thing could be said for the backward edge CFI policy, which handles returns. So again, we're going to trap, otherwise we're going to continue if the label state checking matches. Again, this offers support for both CFI and non-CFI processes and strict enforcement of unique forward edge and backward edge control flow targets. In order to do this, we have to sort of manage the internal hardware in some way. So I chose a mechanism which is just maintaining an internal machine register, which has elements for the CFI label, and it can be extended into those reserved bits at the most significant bits of the register. We have some interrupt service request flags for when the operating system needs to handle requests for switching tasks or overflowing or underflowing the label state stack. And we have some other sort of checks and flags that enable us to moderate requests to the label state stack or label state register, to trigger errors to stop the execution, or even to Bower gate the CFI hardware so that you can sort of lower the energy consumption needed when there's no CFI necessary. You don't need to sort of check CFI. We've introduced these CFI extensions to perform these tasks, these basic tasks. It requires 5. We have a pre-C and a pre-J. So this sets up the call target. And then we have a separate instruction, CFI branch, that sets up the backward edge target. We wanted to do this sort of architecturally independent and not sort of perform any optimization specific to any ISA where I might be able to incorporate the CFI pre-C or pre-J into a CFI branch to make it as general as possible. In order to accomplish, sort of execute these instructions and manipulate them, these guys sort of control the label state register and the label state stack. They allow separation of calls and jumps, right? So there can't be any sort of funny business associated with using a jump pointer from a switch statement as a pointer from a call. And it allows unique labels per targets. And the shadow stack enables returns to only the most recently issued call site. So just as a quick overview, and I'll kind of try to breeze through this, we're going to set up the label state using a CFI BR instruction by pushing a label onto the shadow stack. We're then going to push the label for the return target into a register. This register is dedicated hardware, so we don't have to do any memory dereference instructions. We can sort of access this in single cycle latencies and sort of take advantage of modern out-of-order execution and register renaming to handle this situation as quickly as possible. Once we enter the target, we're going to perform a CFI label check with what's currently at the label state register for a forward edge. Once we then execute, if that check passes, then we're going to enter the function, and we're going to get to a point where we need to execute a return. So that's when the return policy comes into place. The return policy is simply going to look at the most recently pushed label at the top of the stack. So we tightly couple the call and return pairs, and this sort of grows down, right, as you would imagine it would. And it's very intuitive, the idea, right? I make a call from A to B, I make a call from B to C, I can't return from C to A, right, in this implementation, right? So the shadow stack tightly couples these and enforces that I'm only returning to the most recent call site. One other thing we have to take care of is sort of interfacing with the hardware. In order to do that, we have to sort of map a label stack status register to I/O. And this sort of needs to contain information for the operating system to handle the bounds for the shadow stack size, the current pointer of the shadow stack, and to manage some sort of interrupt request routines that we found down the line if we need to context switch during an underflow or underflow. This could be implemented as a machine-specific register so that you don't have to do CPU bus accesses, and you can ensure only privilege access to that instruction. Just in our case, we didn't do that. So to answer why sort of you need hardware for CFI, I think we try to show that in terms of efficiency, you can get improved runtime overhead with dedicated label register and shadow stack. Due to the instruction instrumentation, we have limited eye crash pressure because we're emitting less code and using dedicated hardware elements and register moves. So we could eliminate that sort of degradation in performance overall. We also have reduced decache pressure because we're not setting up some CFI metadata in the program's data space. We have a dedicated label state stack, and that sort of avoids referencing from decache. And the instructions that we instrument that we've introduced are actually single cycle instructions. All we do is we simply toggle the functional units so that they execute as no operation instructions. And then the CFI hardware sort of manages their operations separate from the out-of-order functional unit. And as from a security perspective, we are sort of eliminating a significant number of policy concessions due to the possibility of pointer aliasing analysis and the associated labeling issues. We do this with a runtime points to analysis. We have some isolated memory, which prevents these software shadow stack attacks like stack defiler we presented. I'm not exactly sure of the details for the talk tomorrow, but potentially it prevents that as well. And we have this precise policy enforcement that is agnostic with respect to the labeling mechanism. So if I want to label all of the code in my CFI protected program with the same label, then I have just a basic single equivalence class CFI policy. And I could upgrade that or downgrade that, per use. With that being said, I'm going to sort of introduce Orlando, and he'll finish out the talk for us.
Right. So we have this very nice piece of hardware that Dean here introduced for us. Unfortunately, we need to control this guy somehow. We have to run this on top of an operating system. We have the problem that modern operating systems are actually multitasking systems, and we only have one CFI module. We have multiple processes, though. And plus, we have legacy code, that program you got back in the year 2000 that your business really needs and you can't really replace. So we have a few challenges ahead of us. We need to be able to share this CFI subsystem across multiple processes. We need to keep a separation of processes as well. We need to keep the CFI state for each process independent from each other. We need to be able to handle whatever exceptions the CFI module exposes to us. Plus, again, legacy code, big elephant in the room there. So we have to make a few changes to the way programs run on your computer. So we have a scheduling issue. First of all, have a process that's currently running on the CPU, and suddenly a new process is being scheduled, comes in, it has its own CFI states. We need to be able to handle these things somehow. There is a second case that happens. You have one process running, second process comes in, it doesn't have any CFI state, it's not CFI instrumented. So we have to handle somehow what to do here. Then we have a problem with the shadow stack as well, the level shadow stack. Turns out space is limited, and we have this thing on die built into the CPU. So we do a function call, or the program does a function call, does another function call, and another function call, and another function call, and we still have no returns, and then we do another function call, and we have a problem. We have no more space there. So we run out of stack space. So what do we do here? Well, you could say, yeah, sure, why not? Just get some metrics, see how big you need to make that shadow stack, and see what happens. Well, unfortunately, that's not very scalable. You can't really make these large memories, put them inside a CPU. Plus, you can't also get a whole bunch of programs and say, yeah, my worst case scenario in this set was this, so I'm just going to build it like that. Then there's also the thing that if you need to empty this area inside the CPU, it takes time as well. So if you're copying that in kernel space, you're going to see something like that there. If for some reason you feel like you need to empty that shadow stack and put something else in that place, it's going to take time. If you do this during scheduling, well, your scheduler is now a lot slower. You don't want your scheduler to eat up CPU time that much. So that being said, let's talk some preliminaries here. First of all, a process control block. This is a standard data structure in pretty much every single modern operating system. It's how the operating system kernel sees your processes. If you're working in Linux, you can look in that file in there for task structs. This takes about 1.7 kilobytes in a 32-bit system on Linux. And well, the process control block contains some information about the process, namely its execution state, whether we're running, we're a zombie process, we're suspended, waiting for I/O, stuff like that. It also contains all the memory allocations that the process has made, who owns the process, the group of the process, important, the process ID as well, I/O status information, and well, we also have the CPU context states. We built our CFI module on the CPU, so let's look at that guy and see what we have there. On a modern system like x86-64, you have your inter-racer file, which gets backed up in there every time you do schedule any task. In the Leon 3 processor, which is what we used for implementation, you have a couple more racers that you have to take care of. You have some floating point registers, you have CPU status registers, and well, since we're putting stuff in there, might as well put in all CFI information for the process in the CPU context state as well. So we extend that guy, and every time we do a task switch or something happens with CFI module, we go ahead and modify the kernel to handle that for us. So adding to the scheduler then, we need to see whether our current process is CFI aware or not. If it is, we want to back up the CFI state into the process control block. And the next process that we're about to execute, we check and see whether or not CFI aware. If it is, well, just restore the CFI state. Otherwise, just disable the CFI module. That being said, have some animations here for that. Process 1 is currently running. Process 2 is about to be scheduled. So we see that process 1 is CFI aware. We get its CFI state, push it into the process control block. We check process 2, see that it's CFI aware. Well, just go ahead and restore that CFI state. And now we're free to keep running process 2 as if nothing ever happened to it. On the second case, well, we have process 1 running. We see that it's CFI aware. We are about to schedule process 2, so we back up process 1 CFI state. We go to process 2 now. We see that it's not CFI aware, so we just go ahead and disable that CFI module. We can go ahead and begin executing process 2 now, and no exceptions will occur at that point. However, there's still the stack issue. We already used the process control block for this thing, so we might as well utilize it for this as well. On Overflow, just copy a portion of that shadow stack into the process control block. go ahead and move the top portion of the shadow stack to the bottom. You can do this with a flash copy on hardware. And then you set that little shadow stack pointer to its new location. The underflow process is effectively the same thing in reverse. Got something from the process control block and put it back into the shadow stack, and then again set the shadow stack pointer to the new location. So in an animation there, you can see, go ahead and get the bottom portion, put it on the CFI context on the portion of the process control block, then you do your flash copy, and execution continues as normal. Now, lastly, we need to investigate our CFI faults. There is a control flow violation occurring. Well, the subsystem detects it. Right now, we just go ahead and add an entry on the kernel logs, and then we send SIGKILL to the process. If you're familiar with the Unix way of signal handling, SIGKILL cannot be caught by user land at any point. So we terminate the process. Technically speaking, we could go ahead and send any other signal we want and take actions based on that. There's a few little miscellaneous steps as well that we need to talk about. So you need to have these instructions in your program. So get an instrumenting compiler. Your assembler, of course, needs to be able to recognize these instructions as well. So we extend an assembler. Any assembly code that's in your runtime needs to be patched to include these instructions as well. Otherwise, the CFI subsystem will detect control flow violations unnecessarily. And well, then we go ahead and compile some stuff. And when you do that, you're going to see that. So on average, 1 to 2% performance overhead. And well, relative to the number of calls and indirect jumps that you have on your binary, you're going to see a size increase on your resulting binaries. In our testing, we saw about 13% or so. Now, there have been other guys that have attempted to do this before us as well, so we should give them credit for their work as well. We have Brito et al. In 2006 with architecture support for CFI. However, they only give us a coarse-grained backward edge return policy. Yier gives you also a coarse-grained forward and backward edge policy for CFI as well. This is actually kind of good, but it can be sadly bypassed. We have also HDFI, which won Best Paper Award this year as well. It provides fine-grained forward and backward edge support, but it only does it on single-threaded embedded systems. So you don't have multitasking, you don't have an operating system behind this thing, you don't have shared libraries. And this year as well, Intel released their own control flow policy extension for their CPUs. They apparently have been working on this for quite a bit now. They have a built-in hardware shadow stack as well. They had a new razor for this, the shadow stack pointer. They had a couple of instructions to manipulate this shadow stack pointer as well. However, it suffers a bit when it comes to forward edges. Any indirect jumps or calls in Intel's CFI, they can target any branch end instruction. There is really, there's a coarse-grained policy there. So comparing our approach to the other guys, well, HCFI has some very nice performance overhead. However, they use the Leon 3 processor implementing the Spark version 8 instruction sets. And they use some very architecture-specific optimizations, like putting things on the pipeline bubble on branch instructions and things like that. And well, Intel said the other major implementation, any call or jump instruction can target any end branch instruction that makes it rather weak for a sophisticated attacker. That being said, that's all we got, guys. If you have any questions, feel free to ask. Thank you. Sir.
What's the response of the chip manufacturers? Are they likely to implement this?
Pardon?
Are the chip manufacturers likely to implement this?
So, like we said at the back end of the talk, is that Intel is actually pursuing this, and they're interested in doing the control flow enforcement technology for shadow stacks. One of the issues is a shadow stack, a hardware shadow stack, sort of guarantees this really fine-grained backward edge CFI policy, and an open issue is the forward edge mechanism. I think that when it is released and produced, that potentially, other manufacturers will jump on board, considering that these sort of ROP style attacks are still prevalent and sort of shouldn't be, right? Because there are solutions that can prevent them.
So basically it's a hardware model, and you need to change the compiler, right, to use these instructions. So what about, tail call optimizations? In that case, you will just have a return instruction that says, don't check it.
So in the case of a tail call optimization, this is one of the those nice corner cases that we came across. You effectively have a jump to where you will normally have a call, which means that instead of just going and pushing a value on your regular stack and shadow stack, you just go directly to a new location. Well, the backward dash is actually checked on the original caller. So you call from A to B, but then from B you jump into C. The check actually happens back in A, so we don't really see that issue there. When we do the jump from B to C, we never see that backward edge. We have to return back into B there.
Okay, but the compiler cannot produce any weird code.
So we actually never saw the compiler introducing any weird shenanigans in there, since we tightly coupled our CFI checks to explicitly to calls. When the compiler sees a little optimization it can make there, it eliminates the call. It also eliminates any possible checks that we will introduce at that point for backward edges.
What architecture do you use to implement your?
So we basically. Oh, sorry. Go ahead.
Yeah, and also how do you get? Yeah. Okay. It's fine. Which architecture do you use? Yeah.
So we have both implementations for the Spark V8 and for x86/64.
But this is an instruction set architecture extension, right? So it means these are new instructions.
Mm-hmm.
How were you able to benchmark on the x86/64?
So we run it in a cycle-accurate emulator. We use the so basically we're using a cycle-accurate emulator, and so the performance results are going to sort of vary with respect to actual hardware, right? But in general, there's a long lineage of using emulators and sort of getting semi-reliable results, right? Within, of course, a % error, right?
Okay.
Good?
Yeah, that's fine.
What was your second question?
No.
Okay.
Thank you.
I think the time is out. I think the time is... Okay.
So no other questions?
So,
Yeah, thanks for attending the talk, guys.
yeah,
Thank you.